Welcome back to GG and OCN312. This video we'll talk about the matrix determinant. The determinant is a fundamental and very useful property of a square matrix. It can only be taken on a square matrix, and we'll discuss some uses of it in the next couple of weeks. But in this video, I'll present the basic mathematical formula for a determinant. Then we'll go through some examples with some specific matrices so you can see how to evaluate it. After viewing the video, you will have the ability to evaluate determinants of a 3x3 matrix, a 2x2 matrix, as well as a 1x1 matrix. So let's first discuss some notation. We would denote a determinant by the letters Det, determinant, and we would. So this is how we would denote the determinant of matrix A, and we would equivalently write the determinant of matrix A in terms of each of the elements of A, with vertical bars on both sides. So the first row of A has the element little a11, followed by little a12, all the way out to little a1n. And the first column is a11 followed by a21, all the way down to an1. And you'll notice that I'm writing n here instead of m because a is square. It has to be square. And in this case, it's n by n. And so this is the first column. And then the last row would be an1, an2, all the way out to ann. So this is two ways of writing out the determinant of matrix A. So let's show the mathematical formula for the determinant. So the determinant of matrix A is equal to the sum from 1 to n of little a, j, k, and capital J, k. So little a, j, k is just the element in row J, column K, whatever J or K may be, and capital A, J, K is defined as -1 to the J plus K power and M J K. So capital A J K is what is called the cofactor of element AJK, and we're defining things as we go here. So capital AJK is the cofactor of this element, and it's composed of the product of -1 raised to the J plus K power times MJK, and MJK is the determinant of the n-1 by n-1 submatrix remaining when row J and column K is removed. the last thing we need to do is describe what the sum means. So it means it's a sum on J with K fixed or the sum on K with J fixed. So we could equivalently write the determinant of A is equal to the sum of J equals 1 to n for any value of K. We could pick K equals 1. And that's also equal to the sum, if we sum over K of A, and we could pick any value for J, so let's say 2, K, and then A, 2K. So this is true for any value of K in the first case, as well as any value of J in the second case. Okay, so this is all a little bit abstract, I realize. So it's important to go over some examples. So I'm going to rewrite our mathematical formula up here so we can keep it in mind and relate it to the different parts as we work through these examples. And right, so the sum is from 1 to n of element A, J, K times cofactor A, capital A, J, K, and the cofactor J, K is equal to minus 1 raised to the J plus K power, again, times MJK, and MJK is the determinant of submatrix of the submatrix with row J, column K removed. All right. So let's consider a 2 by 2 matrix. So the determinant of A, and A is a 2 by 2 matrix. So we'll write that. We'll write out the elements as A11, A12, A21, A22. And that is equal to the sum. And as I mentioned before, we could either sum over K or sum over J. I like to sum over K. You can choose what you like to do most, but I'm used to summing over K here. And here it's a 2 by 2 matrix, so K will go from 1 to 2. And we have a 1K and a 1K. So I've chosen J is equal to 1. And again, I do this because I'm used to doing it. And but as I showed before, you can pick any value of J and it would work. You would get the same answer. You would get the same answer. And so let's sum over k. So when k is equal to 1, we have A11 times capital A11, and then k would be equal to 2. So that's A12, capital A12. Okay, so now using our definition of our cofactor, that gives A11 times minus 1 times raised to the second power. I'm going to write that out as 1 plus 1, just to remind us that k is equal to 1, and we've already set j equal to 1, times the submatrix associated with A11, plus A12 times minus 1 raised to the 1 plus 2 power. Now k is equal to 2 again, and then we have the submatrix M12. And so you'll notice that this first term, minus 1 to the j plus k, is equal to plus 1 when j plus k is even, and minus 1 when j plus k is odd. So that's the primary function of this first term. And so this gives plus A11 for the first term, M11, and then minus A12 for the second term. So now let's evaluate the subdeterminant. So in the first case, we have A11. So we're going to remove the first row and first column, and now we just have to take the determinant of this submatrix. So this is these remaining submatrix when the first row and first column is removed. So that's A11 times the determinant of A22. Determinant of A22. That's what the vertical bars stand for, the determinant of A22. And then we have A12 times the determinant of the submatrix when row 1 and column 2 is removed. So that leaves A21. So again, we strike out the first row and the second column. We strike out that, and then what's left is the determinant of A21. So we're getting closer to our solution, and it turns out that the determinant of A is just equal to A. So in the example given, the determinant of A22 is simply equal to A22. And, or I should say, maybe I could write the determinant of the matrix of a 1 by 1 matrix is equal to A11 if, right, so here's our matrix, and this is a 1 by 1 matrix. Formally, we can define a single number as a matrix. It's just a 1 by 1 matrix, and the determinant of that 1 by 1 matrix is simply the value of the number in that matrix. So that's something relatively simple you can remember. And so this gives the result that the determinant is A11 times A22 minus A12 times A21. And I often like to remember the determinant. I do the determinant for a 2 by 2 matrix in this way because I often like to remember it sort of geometrically as the product of the first diagonal going from upper left to lower right. So that's the first diagonal minus the product of the second diagonal. So it's the product of diagonal 1 minus the product of diagonal 2. I'm using the word diagonal somewhat loosely, but if we go from upper left to lower right, multiply those two, that's what I mean by the product of diagonal 1, and then the product of the upper right to lower left term is the product of diagonal 2. And that's equal to the determinant of a 2 by 2 matrix. So as a quick example, the determinant of the matrix made of 1, 2, 3, and 4 is 1 times 4 minus 2 times 3. And that's equal to minus 2. The determinant of the matrix composed of 3, 2 on the first row and 1, 4 on the bottom row is equal to 3 times 4 is 12 minus 1 times 2 is 2, and that's equal to 10. Okay, so the determinant of a matrix is a scalar quantity. It's just a number. So let's look at the determinant of a 3 by 3 matrix. And again, I'm going to sum over k as I did in my first example, again, just because I like to sum over k. And again, I'm going to set j is equal to 1, just as I did in my previous example. Again, I can set j equal to anything, and I'll get the same answer. So we have the sum of A1k times the cofactor 1k, and we're summing for k going from 1 to 3. So that gives A11, capital A11, plus A12, capital A12, plus A13, capital A13. And remembering our definition of the cofactor matrix, that gives element A11 times minus 1 raised to the second power, 1 plus 1 is 2, times the lower submatrix M11, the determinant of the lower submatrix M11, plus A12 minus 1 raised to the third power times M12, the determinant of the matrix submatrix associated with A12, and then we have minus 1 raised to the fourth power, 1 plus 3 is 4, times M13. And that gives, when we have minus 1 squared, we get positive 1. So that's A11. And now remember, we have to remove row 1, column J, and take the determinant of that submatrix. And that submatrix is A22, A23, A32, A33. right? This is M11, the determinant of the submatrix when we remove the first row and first column. So that's this first term. The second term is minus 1 raised to an odd power, so that's a minus, and we have A12, and it's M12 is the determinant of the submatrix when we remove the first row and second column. So that is A21. So we're striking out this second column and first row, and what's left is A21, A23, A31, A33. And then we have minus 1 to the fourth power, which is an even power, and that gives a positive 1 times A, sorry, I forgot to write my A, little a13 here. Make sure we write that here. A13 times this determinant of the submatrix when we remove our first row and third column. So that would be this. So now we're removing this and that leaves this matrix here. And that is A21, A22, A31, A32. And we already know how to evaluate the determinants of 2 by 2 matrices. And so that gives A11 times A22, A33, minus A23, A32, minus A12, that's the second term, and the determinant of this submatrix is A21, A33, minus A23, A31, and then we have a plus A13, and the determinant of that submatrix is A21, A32, minus A22, A31. I should have written a 3-1 right there. And there you have it. The determinant of a 3 by 3 matrix is given as that. So geometrically, we can envision a matrix, again, that's 3 by 3. And the determinant of this matrix, I guess we can sort of visualize it as, well, first we have to focus on, so we have our first term, which is A11. I go by the first row, so I'm keeping J is equal to 1 by the first row, and I'm summing 3 terms associated, which are products or proportional to each element of the first row. So the first term is A11. And then I multiply that by this first diagonal, 1, minus the second diagonal, 2. And so I could write that out as A11 times, I guess, diagonal 1. Let me make that a Roman numeral just to make it more clear what that's a special diagonal. 1 minus 2. So this is the product of 2 elements in diagonal I. Okay, and then the next term, so we subtract the next term, which is this element, and then again we strike out that the row and column of that element. I struck out the wrong column here. And then we have an upper left to lower right diagonal going from from column 1 to column 3, and an upper right to lower left diagonal going from column 3 to column 1. And so that gives A12 times I minus the second diagonal. And then we add to it the result when we take the third element of the column, and then again we cross out the row and column of that element, and we multiply from upper left to lower right the two elements in diagonal 1, and from upper right to lower left the elements in diagonal 2. So that's A13, 1 minus 2 there. Oh, and I forgot to mention for the first case, we struck out the elements in the first row and first column associated with A11. So this is one way of sort of geometrically illustrating how I remember how to do a 3 by 3 matrix. And this might be useful for you as well. So I'll conclude with an example. Let's say A is equal to 0, 2, minus 1, 4, 3, 5, 2, 0, minus 5. And the determinant of matrix A, and I want to make sure I put the double bar to denote the matrix. And this was important to distinguish the matrix, of course, from the cofactor A, right? We have a matrix A, and we have to distinguish that from capital A without the double bars for the cofactor. So the determinant of matrix A in this case, get back to where I am, is equal to, so first we have A11, which is 0, times the determinant of this submatrix, which is 3 times minus 5 is minus 15, minus 0 times 5, which is 0. Actually, let me be a little bit, let me do an intermediate step. So it's the determinant of 3, 5, 0, and minus 5. And then we have minus A12, which is 2, times the determinant. Again, we're going to strike out the column and row that element 2 is in. And that's the determinant of the matrix 4, 2, 5, minus 5. And then we have a plus minus 1, which is the upper right element. And when we remove the first row, third column, we're left with the submatrix 4, 3, 2, 0. And so the solution is 0 for the first term, minus 2 times 4 times minus 5 is minus 20, minus 10, and then we have a minus 1 times 4 times 0 is 0, and we have a minus 6, and that gives minus 2 times minus 30 plus 6, and that's 66. So that was the determinant of this 3 by 3 matrix. Okay, so that wraps up a discussion of the formula for a determinant and some examples of how to evaluate determinants. Again, for a 3 by 3 matrix, a 2 by 2 matrix, and the 1 by 1 matrix is very simple.